Great, thanks for joining the Freshwater Trust today for our webinar. I'm Danielle Dumont, and I'm going to be giving you a few quick introductory notes. Today we're going to explore some new tools for watershed assessment and management of restoration programs. And before we jump into that, I'd just like to give you a few quick housekeeping notes. So if you'd like to participate and ask a question, at any time you can do that by typing it into the questions box that you're going to find on the right-hand side of your screen. Also on the right-hand side, you will find a handout about the BasinScout tool that you can download if you are interested in doing that. Also, just want to note that this webinar is being recorded and we will make it available for review at a soon later date. So if you'd like to listen to it again or share it with your colleagues, you'll be able to do that after today. I'd like to introduce the presenters that we have. First, we have Alex Johnson, and Alex is a Senior Freshwater Solutions Director here at the Freshwater Trust. Well, I have a screen that shows Alex, but it seems to be delayed for the audience. There we go. So Alex is joining us. He's a Senior Freshwater Solutions Director here at the Freshwater Trust, and over the past 6 years, Alex has been closely involved in the analysis, the development, and implementation of some of the first water quality trading programs in the Pacific Northwest. He has worked directly with private and public entities to build some natural solutions that can both successfully achieve compliance and watershed restoration. Joining Alex, we have Julia Bond. And Julia is an Ecosystem Services Analyst here at the Freshwater Trust. Over the last several years, she has provided key analytical support for water quality trading programs, conservation actions, and policy work. And Julia's work has allowed her to dive pretty deep into some environmental data and modeling. Those are who are joining us today, and I'd like to turn it over to Alex now, and he'll give a quick overview of the Freshwater Trust. He'll share with us the agenda, and then we'll dive right into the tools. Alex, take it away.
Thanks very much, Danielle. This is Alex Johnson. I really appreciate everybody joining us today. We're definitely excited to have a lot of new names and new states, new regions on the webinar. So thank you very much for your interest. We hope to really make it valuable for you. Certainly, since we've got those new names, we want to give you a little overview of the Freshwater Trust. We are a 32-year-old 501c3 private nonprofit organization. Our mission is freshwater conservation and increasing the pace and scale of how we can benefit our freshwater ecosystems. And we've got a long history in large-scale river restoration, as you see on the left of the screen there. Have done a lot of side channel reopenings over the years, increasing sinuosity and putting in log jams in different places. A lot of restoration here in Oregon, where we are headquartered, to benefit salmonid populations. We also started as the Oregon Water Trust, the first water trust in the United States about 26 years ago, and maintain a lot of capacity and expertise in flow restoration. So we have quite a few project managers, especially out in eastern Oregon where it tends to get quite dry, that are working full-time with landowners to purchase or lease some of their water rights to keep rivers wet at the right time of year for fish spawning. So that work, again, as I said, we've been doing for many decades, both of those two activities. And about 5-6 years ago, we were stakeholders in a process here in Oregon that clarified a lot of the protocols, mechanisms, and quality standards for a Clean Water Act compliance solution called water quality trading. Shortly after the stakeholder process, where we were one of the conservation nonprofits kind of putting in our input on the quality standards and what we would want to see, in this case, from riparian restoration for temperature credits for Clean Water Act compliance, we found that the utilities here in the region that were really wanting to look at using one of these programs for compliance didn't have a service provider. So as a now 50-person nonprofit, we were large enough and regionally focused that we thought it was certainly part of our mission to jump into that space, and for 5 years now we've been partnering with municipalities, hydropower operators and others to figure out what kind of watershed programs they could design and implement to comply with different allocations from the Clean Water Act. So some of these tools, if not a lot of these tools, have been developed to help our work in that space, and we see a lot of other applications that we will go through shortly. Looking specifically at water quality trading, just to give, I guess, a little bit more background on why these tools look the way they do, critical for a utility that is looking at a watershed solution for compliance, usually from a temperature allocation or even more likely, especially nationally here in the United States, a phosphorus or a nitrogen waste load allocation. There is a lot of upfront effort that needs to go into analyzing the watershed, looking at where are the input points for those water quality parameters, be it temperature, phosphorus, nitrogen, sediment, etc. The way that water quality trading works is that those dischargers that are being regulated, instead of upgrading at their point of discharge, they can look to some of the other places in the watershed, what we call non-point sources, and some of the inputs that are coming in of phosphorus or temperature, what have you. And instead of upgrading at the plant, they can go and work with those private landowners usually to implement restoration or conservation actions on those farmlands usually. So that not only has forced us to develop our capacity to analyze a watershed, but also to work within a lot of different regulatory structures now within Oregon, Idaho, California, and Colorado, where we have active analyses. And then, as I said, our organization now also is a service provider for the implementation of these programs, using these tools, and as you'll see, developing new tools to help us better and more cost-effectively put restoration actions on the ground in the places where they are most ecologically beneficial as well as cost-effective. So that's kind of to set the table on the Freshwater Trust, and certainly the point of view that we come at. We see a huge amount of need out there, I think, for better use of dollars that are spent on conservation, and in some cases, like the one I just explained, where dollars are being spent ostensibly for the watershed's benefit, but they may be getting spent on gray infrastructure that on a cost per unit basis is not the most cost effective. So these tools can help underpin the better expenditure of those funds in a more holistic manner throughout a watershed. So looking at our agenda then, and hopefully we can really clearly demonstrate how these tools can be used as such. First, we want to go over to southwestern Idaho, where we have quite a few municipal clients, as well as a hydropower utility that we're working with, and we're going to look at a pretty interesting phosphorus and sediment reductions analysis that we performed in the lower Boise River. Julia Bond will be walking us through not only that one, but quite a few of these, and some of the public data sets that we used to combine and provide a graphic output that makes it a lot easier for decision makers to see not only that a watershed program is feasible, but that it is cost effective and a really good use of their public dollars. Then we're going to come back to Oregon, look at a riparian disturbance analysis, and that really was what set the stage for us in our largest riparian revegetation project, which is down in the Rogue River, and then work from not only that initial analysis, which was looking at how are the riparian zones doing, but then how and where do we implement those sites to best generate temperature credits, in this case, for our municipal partner. And then look at how we track that program on the watershed scale as we're implementing it, as we've been doing for the last 4 years. We'll touch on the StreamBank monitoring app, which is an application that our field staff uses when they are out in the field, especially collecting photo points and other metadata to demonstrate that the sites that we are implementing are reaching the quality standards that are required over time to generate these credits. Then we'll move into a recent grant-funded prototyping effort that we undertook that is a groundwater budgeting and trading prototype, this time down in the Salinas Basin, down in California. Walk through kind of what was the ask there, what was the idea that led to that, and the output that we're pretty excited about and has quite a ways to go as well. And then a quick example of how these things that have been mostly looking at in-stream water quality and especially surface water runoff could also look in an MS4 or a stormwater context. So lot to get through. We will move fairly quickly, but again, this is going to be recorded, and certainly ask your questions while we are speaking, and Danielle can help us in the last 10-15 minutes to walk through those questions and hopefully answer those. And of course, our email addresses are readily available, so please don't hesitate to circle up with us, shoot us an email or a call after this if you have any further questions. So thank you very much again for your interest, and I'm going to pass it on over to Julia Bond, who's going to walk through that first item, which is the phosphorus and sediment reductions analysis.
All right, great. Thank you, Alex. So let me just get my map open here in just a moment. I'm going to spend a little bit of time, like Alex mentioned, working through an example in the Lower Boise River watershed. So this is a watershed in southwestern Idaho where you have a number of different municipal sources that are all interested in figuring out different ways that they might be able to meet some of their new permit obligations that they have in their discharge permits and their NPDES permits. And you also have a really interesting watershed where you have this combination of an urban landscape that's continuing to develop and a historically agricultural dominated watershed. And what we had in the Lower Boise is a recent total phosphorus TMDL that was just recently, it's actually right in the process of being finished right now. And with this new total phosphorus TMDL, you have new limits that are going to be set within the watershed, and they're designed to try and address in-stream conditions on the Lower Boise. And what you have on the Lower Boise is some pretty serious issues with water quality, particularly in the lower stretch of the river. So here we have an example of Mason Creek, which is a tributary of the Lower Boise. Right here we have the Lower Boise flowing in this direction from the right side of the screen to the left side of the screen. And right here you'll see this rather brown-looking tributary flowing into the Lower Boise, and you have this nice sediment plume that's coming into the river. And when you're looking at a reach like this or the watershed, you're seeing some pretty substantial non-point source impacts that are coming in large part from the agricultural practices within the basin. So in this particular basin, we have a large amount of surface irrigation. So that is irrigation water that's applied directly to the field in a large quantity, and in some cases it can result in some pretty substantial erosion, and you see a lot of runoff coming from the individual fields, and it's carrying with it all sorts of sediment, nutrients, and particularly phosphorus associated with that runoff. And it's in many cases just being discharged directly into the Lower Boise, resulting in impacts downstream where you have nuisance algal growth and some impaired water quality downstream. So the question that we wanted to ask was, all right, if we're looking at the Lower Boise and we want to improve water quality, and if we want to support water quality trading in this basin, where could we implement agricultural conservation practices, best management practices on these fields to try and improve the in-stream conditions? So where could we see reductions in sediment loading and reductions in the associated total phosphorus loading with those improvements? So looking at the watershed, we wanted to use the available information, and we had a large number of public data sets that were available to us in the Lower Boise, and we were taking all of these different pieces. And the first one that we're looking at is the digital elevation model, so looking at the topography of the basin, and using that we calculated the associated field slope for each individual field in the Lower Boise. We delineated the boundaries of each one and then calculated a number of different statistics that would then be used in the modeling component that I'll talk about shortly. So the first one is the field slope. So slopes that are steeper are more likely are higher erodible fields. So you're going to see more runoff coming from these steeper fields than those shallower ones, which are the green ones that you see on your screen here. Those darker ones, typically, you see them a little bit further away from the river. The river is going right in the middle of the screen right here. And so that was one of the key pieces that we brought in, one of the first data sets that we used. The next one that we wanted to look at was the soil on these different fields. So using the NRCS soil survey data, using what's called the K factor, and that's an erodibility factor. So how likely is it for that soil to erode? The darker colors on your screen are those soils that are more erodible compared to the lighter colors on the screen. Those are the soils that are less erodible. So we've got a number of different data sets that we're pulling together to try and assess the conditions on each one of those agricultural fields. And as you might imagine, crop type is pretty key when you're looking at what's going on an individual field, so those agricultural practices that are being employed. And right now we have a snapshot of the 2014 crop data that were used as part of this effort, and that's information that came from the USDA. And these have been categorized, so those yellow color that you see, that's row crops, so things like corn. Your permanent cover, that blue color, those are crops that are grown continuously for a period of time, so that's something more like alfalfa, hay, and then you have those intensive crops, which are the purple colors that you see on the screen, and those are things like sugar beets, potatoes, onions, commonly grown in southwestern Idaho, and these are intensively grown row crops, so they, as part of the agricultural production and the management practices that are associated with these crops, they involved a lot more disturbance of the soil. So it results in far less residue being left on the field at the end of the year compared to things like alfalfa that is far more closer growing type crops. And so not only did we use the crop types for each individual year, but we also did a look back. So 1 year previous to see what sort of residue you might be able to expect left on the field after the harvest. And that has an impact on the type of runoff that you would also expect, having more resistance left on the field if you have residue left on that field. So pulling together all of those different crop data layers, we had about 10 years altogether worth of crop data for this particular analysis. And then the other key piece that we needed to be able to identify was the irrigation type. I showed you that picture just before of that eroded field where you have surface water runoff coming off of an individual field. So we wanted to look at those fields that were actively being irrigated through surface irrigation and those that were being irrigated through a sprinkler system or some other pressurized system. So the blue fields that you see on the screen are those that are sprinkler irrigated, and then the rest are ones that are surface irrigated field within the surface irrigated fields within the basin. So the key here was to take all of these different layers, all publicly available information, and combine them. What we wanted to understand was if we're going to be trying to target our investments within this watershed to the agricultural fields that are in most need of best management practices or changes to practices in order to reduce sediment and the associated phosphorus loss, then we wanted to make sure that we were targeting those fields as part of our analysis and understanding where they were and what the associated phosphorus load was for these different fields. So what you see on the screen now is the mean total phosphorus load from each one of those individual agricultural fields within the basin. The lighter colors that you see on there are those that have less of a total phosphorus load associated with them compared to the darker ones where you have more. And in some cases you have some pretty substantial phosphorus loads that are coming off fields, and those will typically be those highly erodible soils along with steeper slopes and more intensive management practices associated with the crops that are being grown. And that's where you see the different colors on the screen. And that allows us to figure out where we want to go and interact with the landowner. We refer to it as uplift, so that's the environmental benefit associated with the management practice. And you can see your darker colors are your high potential, so where you can see the most reduction in total phosphorus associated with an individual practice or on an individual field. And if we select a single field, I just give you an example when we zoom in here, that yellow field, we have a whole host of information that's associated with that individual field. We understand who owns it, we have acreage associated with it, and we also can look back at the crops that were grown on it, and we get some estimates for what the current sediment and phosphorus loads are, and then the potential benefits that you would see by changing irrigation practices, implementing no-till, filter strips, all of these different BMPs that would allow us to target where we could see the most benefit, so the best water quality benefit associated with a conservation practice. And so with that, I was going to turn it over to Alex here at this point, who's going to give us a little bit of an intro.
One question before we start. Julia, we had some questions come in as you were explaining the map that you just showed, and folks wanted to know perhaps where the sources of some of these agricultural layers were from. such as the land use layer or the irrigation type layer. And could you maybe answer that real quick?
Absolutely. So so if you're looking at the crop information, that crop data came from the USDA. They have an annual source of crop information for the entire United States. It's referred to as their CropScape data set, and you can go to their website and download all of that information for whatever years they have available and for an area of interest that you have, and that's categorized by individual crops. So corn, soybeans, potatoes, onions, all of those things, and that's released annually. For the parcels that we're looking at, we have two sets of information here. One of them is the specific boundaries of those individual fields, and those were hand delineated using aerial imagery. So each one was delineated by hand to get the boundaries of each agricultural field. The ownership information comes from the county that's the tax lot information from the county assessor's office. So we had 2 counties in this particular instance, and that's where the ownership information comes from. So all of these are publicly available data sets that could be downloaded in most cases for free, and the only ones that you sometimes see that require payment would be for something like tax lots. Sometimes a county assessor's office will ask you to do so. And the model that we're actually using to generate this information is referred to as the surface irrigation soil loss model, and it's a modified Russell, so revised universal soil loss equation. It's adapted specifically for southwestern Idaho to deal with some of the conditions that are specifically here, and so that's where all of the sediment and the phosphorus modeling results are coming from for this particular one. All right, and so with that.
All right. Thanks, Julia. And I think important for especially the viewers to understand, we certainly would love to talk with whomever about how to develop tools and models like this. We've had a fun time over the last 5-10 years developing our capacity to do that. But I think the gist of this webinar is that this is a lot of these data are really readily available now, and demonstrating it like this graphically is not rocket science. And I think there's quite a few entities out there that can help do that, and from our conservation mission perspective, it's a lot better way to think about how you're spending your conservation dollar. When we think about big, scary problems like the Gulf of Mexico having a dead zone, or a lot of the different non-point runoff issues that we see pretty much everywhere in the United States, looking at them on a whole makes them seem intractable. But when you can break them down to specific fields like this and really clarify where a lot of that is coming from, that helps you kind of move forward as a conservation actor, whether it's a government agency, an agricultural agency, or in our case a municipality looking for reductions to really find where those most effective places are. So as Julia said, I'm going to take you over to the Rogue now, and certainly we'd love to answer some of your questions on the phosphorus side at the end of this session. But the Rogue is where we've really applied some of this watershed analysis. As Julia said, we're really just in the feasibility stage for phosphorus out in southwestern Idaho. So we have quite a few different clients looking at what reductions they could get from working with those landowners to install agricultural BMPs. In the Rogue, we're now 4 years into implementing one of those water quality trading programs. So the city of Medford, in this case, started working with us 5 years ago to figure out if a program to generate riparian shade would be cost effective for them versus some of the other alternatives, which included a settling pond and chillers. And what we were able to demonstrate was that it was feasible and very reasonably priced versus the other options. So how were we able to do that? And that's kind of where we get to the watershed assessment that Julia will walk you through. Again, using data layers that were out there, a little bit of our own hand digitization and GIS work certainly, but nothing way outside the box. And that really helped us as basically the designer of the program to feel comfortable that the assumptions and the assessments were good. And then now as an implementer, we're using those same data layers to prioritize where we put restoration and then track over time how it's benefiting the river. So I'm going to pass it back to Julia to walk you through that example.
Okay, great. So here we are. We're in the Rogue River Basin. We flew a few hundred miles to get to the Medford area, and I'm going to zoom in on a specific tributary of the Rogue River Basin. This is the Applegate River here in southern Oregon. And so the question here was, if we're looking at a water quality trading program for the purposes of improving thermal conditions within the Rogue River Basin and its tributaries, we're looking in this case at improving riparian conditions. So the question that we had was, all right, what sort of information is out there and what can we use to identify those current conditions that are within the riparian zones within the basin, and then what sort of potential benefits, what sort of shade could we actually be able to produce that could be then used to build a water quality trading program. So in this case, we're looking at the Applegate, and we wanted to understand those, those riparian conditions here. And what we've got is the first data set that we used is a LiDAR data set. So that's some information about elevation, and we can develop a canopy model from that. So that gives us an understanding of the height and conditions of that riparian vegetation along the banks of the river. And here's just an example, as you can see on here. What we've got is the watershed has been, the riparian zone, the vegetation conditions here have been characterized using different height classes. So the blue represents taller vegetation, whereas that gray represents very short vegetation. And this is really important for the purposes of modeling shade, because we need to understand where we have current shade and where we could potentially improve riparian conditions through planting projects. So using this information to get us started with understanding those vegetation conditions. We've also adapted this method as well where we don't have LiDAR data available, because unfortunately we don't have it in all of the watersheds in which we're working. And so we can get around that by doing some hand digitizing work to evaluate current vegetation conditions using some field visits in some cases, but then also using aerial imagery to identify where vegetation currently exists and associated condition of that vegetation. So are we seeing invasive species there or a nice riparian canopy? And so using that information, what we've done is we use a model here. It's the shade module of the heat source model that gives us an understanding of shade conditions along the banks of a river. And so we take that current conditions information, so what do the trees look like now, and then we project a future condition. What will that site look like after we plant trees and they've grown and they've matured over time? How much shade will we be able to generate? And the key here for us was understanding where do we want to see these actions on the ground? Where will they be most beneficial in improving conditions of these riparian areas within the basin? And so what you have on your screen right now is what we like to call our red, yellow, green maps. So what you have is riparian conditions and the potential improvement associated with those, but actually subdivided by tax lots. So we understand not only where we could see improvement, but the ownership of that, so that when we're going out and we're talking with landowners and asking them whether or not they're interested in participating in a project, we know the people that we would like to talk with first, those who have areas with the most potential, and understand what sort of uplift, what sort of environmental gain we could get from a project on that site. So in this particular example, we've removed some of the specific landowner information for some privacy concerns, but what you have here is we understand who the owner is, and we understand the potential benefits associated with it. We have an understanding of the size of the project, and then right here we have kcals, so millions of kcals. It's a unit of energy. In this case, we're talking about a reduction in solar loading. So we have close to 20 million kilocalories per day of improvement associated with this approximately 2-acre site within the Rogue. And this gives us an idea and helps us with our prioritization and helps us with the work with different landowners and how we can implement our project as effectively as we can, which Alex is going to go into a little bit more.
Thanks, Julia. So as Julia mentioned, this is certainly quite a lot of work, but what was very necessary before we, as a nonprofit organization, signed up to implement riparian re-veg in the Rogue, we needed to know that it was possible, and certainly the City of Medford needed to know that as well. So we now have hundreds of miles of digitized stream banks and shade calculations. And then what you're looking at now is a back end that we've developed for our recruiters down in the road, our landowner recruitment professionals and project managers, so that when they, and again, we've anonymized this, but when they are looking at these sites, they're not all the same. We have estimated the different costs as well as the uplift that are coming from those different sites, and basically this type of backend it's a multivariable optimization tool on the back end here that is not only going for the kilocalorie goal so that we achieve the temperature reductions that we need, but we're also trying to stretch the mileage as much as we can, and then we've also tinkered with and are using some prioritization of getting close to fish habitat, active spawning ground, and also closing some of the riparian canopy where we can. So using this to really make the biggest environmental bang for the buck, and on this spreadsheet, it basically, once you choose to implement a site, you can understand how much closer you're getting to those goals, as you see kind of going in the upper right-hand corner there. And then that all rolls up as we're selecting sites and recruiting them. That all rolls up to what we've mocked up here as kind of the program tracking for temperature, in this case for compliance. So what you see is the current kilocalorie load on the Rogue and the target kilocalorie load on the Rogue in 2023. Basically, we have 10 years to generate temperature reductions to get that facility, or to keep that facility in compliance with their NPDES permit. So we've mocked up here not only what we expected or what we estimated we could implement and generate credits to, but then now that we have 3 years of implementation, we have post-project calculations on the credits that we were able to generate. And then I think importantly, there's a third party associated with generating water quality trading credits, and so because we have a lot of information that was generated for those third-party certifiers and verifiers, we want to demonstrate that as well for the decision makers there in Medford. In this case, Rogue River Mile 128 was our first site. We know how many temperature benefits were generated by restoring that site. We have some description of what was done and where. Very importantly, the amount of credits and what model we use to generate those credits, and then we have a quick link to the third-party website, in this case Market Environmental, it's used a lot in the carbon world. We use it in the temperature credit world to host a lot of the documents that are required in Oregon to make these credits valid. So you'll kind of see the whole list here. Really starts with validation. Is the site valid to generate these credits? There's some quality standards associated with that. We want to make sure landowners aren't cutting down all their riparian vegetation so that they can get paid to allow it to be revegetated. Once we implement, there's project design descriptions, we get a third-party verifier in, and then each year we come back and we develop a monitoring report. Looking at a monitoring report, just a quick example here, this is one of the second-year monitoring report for that first-year project that we did. I think what we want to demonstrate here is that there's a lot more information that we need to gather on if this project is being successful or not. We, especially being around 30 years, we've done a lot of riparian revegetation. The quality standards from especially grants and philanthropic donors are never as robust as they have been for water quality trading programs, because if a riparian site is restored and the temperature benefits are necessary for Clean Water Act compliance for the next 20 years, then of course that is a little bit higher bar than have you fulfilled the basics of a grant application. So I think what we're trying to demonstrate is that certainly the quality standards are quite robust, and we are gathering a lot more data than we ever have in our history. So Julia actually is going to walk through some of the ways that we gather that data just in a couple minutes. We've built out an application that our monitoring staff now has on iPads, basically to condense a lot of the different objects, the camera, the GPS, the other things that are out in the field. A lot of that, especially on your second, third, fourth year monitoring event, you can put all that on an iPad, and we now have an application where we can update monitoring protocols on the fly and really help QA/QC while those monitoring experts are still in the field. So I'll turn over to Julia. We've got some good questions coming in already, and I promise we will get to them.
Great, thanks, Alex. So as Alex mentioned, we've been collecting a lot of information with these different project sites, and we found that we were spending an enormous amount of time just coming back to the office and entering all of this information into our databases, and we realized we could cut a lot of that out by developing an application. So I'm just going to give you a quick little tour of this of the StreamBank monitoring application that we've been developing. It's designed to use with the iPad, and it allows our field staff to go out in the field and take consistent information year after year. So in this particular example, it's one of our project sites down in the Rogue, and we collect a whole bunch of different information with these. We collect information on vegetation progress, so this is the number of trees, which species are out there, percent invasive, all of those different characteristics, and how everything looks. So what's the vigor of these different species? Are they being eaten by something? All of those different components. And then I think the compelling piece that we capture year after year is what we refer to as our photo points. So this is taking a photograph, multiple photographs of the project site year after year in order to document that progress, that growth over time. And for something like a riparian revegetation project, those changes can be pretty dramatic. So in this case, you can see the previous year's, the first year, so right after the project site was built, and then you can see how it is progressing over time. So in this particular example, you can see what it looked like when it was first planted. You can see all of the trees, how they're doing, and then you can see 1 year later, after one growing season, you can see the change. We have a lot of excellent growth, and with the iPad, we can take the exact same picture really very, very consistently year after year, and being able to line everything up in a way that we wouldn't actually be able to do as easily if we had to bring out printouts of each different photo point into the field and consistently try and take that same photograph every single year. So really just a number of useful features that you can get when you switch over to using something like an iPad to collect your field data. And so
yeah, and I think where we're seeing, certainly with the applications that we're developing, is as they get easier and easier, we are beta testing with a lot of different third parties here in Oregon, land trusts and watershed councils, and the technology, as I'm sure you're all aware, if you have an iPhone or any other type of smartphone in your pocket, the technology is getting to a place where we think that quite a few monitoring apps or monitoring tools can get simple enough that we could even ask landowners to be a part of the monitoring and obviously save some costs there, but basically get geo-referenced pictures and other metadata from landowners on restoration actions. So anyway, that's kind of the whole suite of tools, I think, that we really developed to help implement our temperature program, and it's in only the third year of 10. But certainly we see as some tools that can also help answer some questions, not only for water quality trading programs, but some of the questions that we're coming across when talking with large agribusinesses that have sustainability goals and are kind of wondering how to set those and how can they prove or claim that they are capturing new sustainability outcomes. It seems like a lot of the tools that we just walked through in terms of the phosphorus benefits, the temperature benefits, and how you kind of interact with landowners could be really helpful. So we're going to switch over to a groundwater budgeting and trading prototype that we developed. And we did have a question come in that I can speak to right now, especially I'm sure it'll come up when you look at this. And it's very basic. How does the ag community, how sensitive are they to the results like that we've seen and that we will see here being associated with individual landowners? And obviously we think about that a lot, as everybody does that works on conservation programs. I think our comfort level is pretty high with the agricultural sector because for so many years we have contracted with individual landowners on their in-stream water rights. Obviously a very touchy subject, some of the most valuable pieces of their land. But for 20 years we've been successful in transacting those water rights, and it's really by being very clear about why you are talking to them, why you're there, what amount of money and what the contract would look like if they were to go down that path, and really helping them as small business owners make a very business-oriented decision on if they want to pursue a conservation contract or not. We think very similarly in looking at our temperature credit programs, and I think the benefit that we see from some of these models is that we never put up an ad at the Grange Hall and just talk to all of the landowners. We literally only have talked to in 3 years maybe 15, maybe 20 landowners out of 1,000 or 2,000 that might have riparian zones in the Rogue. So this allows us to pinpoint and only talk to those landowners that we know we want to talk to. When our project managers show up, they have a clear contract and they know how much they can offer to get a lease, for example, and restore that site. And I think, lastly, and you'll think about this when you see this groundwater map of the Salinas, I think that it's important for our sector, the environmental sector, the conservation sector, to start using these publicly available data and making them publicly available and demonstrating that there is a lot of knowledge out there already about what's happening on fields. I think back to when Google Street View started showing my house. For a couple days, that was weird. Anybody could go type in my address and see my house. Very quickly, I became used to the fact that that was out there. I kind of feel the same will happen eventually in agriculture, where we're just combining public data sets and showing graphically what's happening. And I think agriculture, especially every farmer that we're working with, and a lot of the businesses that we're working with, they see that these problems are real, that they're contributing to them, and they want to be part of the solution. And so this really helps demonstrate that that does not mean that they're going out of business, but rather that there is a good path towards them being part of that solution. And a lot of times that they can find conservation incentives to help them do these upgrades and do them right. So Julia, I know we don't have, let's see, probably 7 minutes or so to work through this, but basically we were, especially because of some of the other work that we've done in assessing and prioritizing actions through a watershed, we were lucky enough to work with the Rockefeller Foundation earlier this year on an idea that has become what you're going to see, the BasinScout for groundwater in the Salinas, and basically asking the question of, with the new Sustainable Groundwater Management Act in California coming in and potentially being a cap on groundwater pumping, how could we kind of make that effort most successful, especially in working with agriculture? How could we kind of protect not only agricultural revenue and jobs, but also really increase the environmental benefits of decreasing groundwater pumping and certainly decreasing nitrate in the groundwater as well. So Julia will walk you through some of the data sources that we used and what a scenario looks like that comes out of this prototype.
Right, so what we're looking at here is our Salinas BasinScout tool, and this was, as Alex was just mentioning right now, it was designed really to try and help decision makers when thinking about groundwater use within the Salinas Basin in California. And we had a number of different components that we wanted to use, a number of different data sets, using crop data again for this area, using elevation information, landowner information associated with different ranches and operations within the area, and then also pulling together other data sets like evapotranspiration to try and understand water uses within the basin itself. And so I'm not going to go through all the details of all of the different components, but what I want to emphasize here is that there's a lot of different options and a lot of things that can be incorporated into a decision-making tool that can help folks understand the options and the trade-offs that are associated with making these different management choices. So, for example, putting a cap on the amount of groundwater pumping that can take place within the basin, and then how also you might affect municipal water use. And then, like Alex was talking about, this is really designed to help you understand your priorities. So if your focus is on ensuring that things remain profitable, that you're not changing things within your basin so dramatically that you're no longer going to be profitable with your agricultural practices here, or if you're concerned about jobs, or more specifically about water quality concerns. And you can weight these differently depending on what you're trying to accomplish and the different goals that you have within your basin. And then of course there's a number of different tools that you can use to try and help with allocation. Cap and trade as an example, a fee, user fee. All of these different options can be used to try and help you understand the impacts of these different decisions. So you can also try and protect the characters within the basin. So do you want to make significant changes to the agricultural practices that are going on, or do you want to try and keep characteristics as similar as possible? So in the background, what's behind this interface is an optimization process that takes all of these different components, weights them, and then uses all of that information to develop an optimal scenario. And it's purely based on the inputs that you're using, and it's based on the characteristics of the basin, and it's not necessarily a scenario that you would, or that your managers would go out and implement, but it gives you an understanding of the impacts that you could have by making these different trade-offs. So what you have on the left side is the current conditions. You can see the crops that are currently being grown, and on the right side is the result of your scenario. So our choice to equally weight profit, jobs, and nitrate hazard all within the same scenario, and then also restricting the amount of groundwater pumping that you're using. So you can see you have a reduction in the amount of water that's being removed from the basin, a change in the acreage that's under production, but you have an increase in profit and a decrease in your nitrate hazard. So your water quality impact can go down if you were to implement this particular scenario. And you can also see how it impacts some of the dominant crops that are being grown or suggested to be grown within the basin. And all of these things, you can run multiple scenarios, compare different scenarios, gives you that information that will help you make those trade-offs and help you understand the impacts that you might be making with the different decisions.
Great. And I think important here is that this is not meant to be a regulatory tool for agriculture, and I think that's certainly what pops up in people's minds when they first see it, but certainly one that can demonstrate how different production decisions by a whole lot of different fields working in conjunction towards a goal can get us to a place that's more sustainable. So just because I kind of wanted to show that each one of these, again, is hand digitized and overlaid with the data sets that Julia was speaking to. So we know how many acres, we know the dominant crop, and if we established incentives that basically valued the amount of groundwater that you were pumping, so that if you were pumping less than the cap, you could sell off that allocation to another owner. Where that would end up is a lot less broccoli being grown and a lot more berries, for example, and a little bit more grapes, and that would have those impacts there. We chose the Salinas because there's copious amounts of data there. I think that's important to note. In places that don't have the groundwater monitoring that the Salinas has, and a very recent model on how that groundwater and nitrates are working within the basin, this would be more difficult, but I think you can make some assumptions based on a lot of the data that are out there and pull them together in this type of way. And again, as Julia was saying, it's a big spreadsheet that backs this up, that finds the economic term would be Pareto optimality, but basically the point or series of points along a curve that fits the needs of the user, or the priorities that the user just input. So anyway, we think a really interesting example of how not only can profits and jobs be still valuable, held to be valuable, but also you can reverse some of the over-pumping of groundwater in some of the basins, especially in the West, that are facing these problems. And then just very quickly, we did mock up just recently what a stormwater prioritization tool would look like. We read quite a bit of the San Diego stormwater regulatory documents and found that this creek right here that it's pointing me to is one of the high priority places. We know that from some colleagues in the field, we know that San Diego is considering a stormwater trading compliance alternative for MS4s. And we just wanted to demonstrate, using these same types of tools, what that would look like, where a user or decision maker or potential implementer of stormwater actions could go in and take a look at kind of the different BMPs, in this case a retention pond, the amount of gallons retained by those types of BMPs, some basic numbers on phosphorus and nitrogen benefits of retaining that water, and just see that, you know, in terms of cost per unit, the red ones in our scenarios are the ones that are the most beneficial, or the highest bang for the buck, and some of the yellows and greens are a little bit less economically and effective. So anyway, just wanted to show that. I know plenty of folks are working hard on stormwater solutions, and we can see how these same types of outputs could help answer some questions and kind of guide how a stormwater program would look in a more urbanized watershed than we're used to dealing with. From our history, we certainly have worked a lot more on agricultural fields. So that kind of gets us through the broad suite of tools that we've developed to help manage some of our own programs and to really demonstrate feasibility of watershed programs to meet either conservation goals or compliance goals. So I think Danielle's going to switch it back to our final slide here. And so we do have about 10 minutes that Julie and I can get to some of your questions, and I definitely appreciate it, all the different questions that we've gotten. So since I've got the mic, I may as well start, and then I'll kick it over to Julie. I see she has a couple as well. So on the couple questions on the monitoring app, was the difficulty, what was the difficulty to create an app, and also how do third parties use it? We seeing the need from our own staff, that a lot of our monitoring staff were spending a lot more time in the office QA/QCing data and downloading data. We really did it for our own use. We use third-party developers. We have somebody that manages those developers in-house, and basically have built a beta suite of apps. We are now partnering with a couple different utilities. eWeb is one of a drinking water utility down in Eugene, Oregon, that we're working with them on building this app out to support what they call a voluntary incentives program, or a source water protection program, and they want their land trust and some of their partners, when they go out into the field, to be able to quickly judge the quality of the riparian zone. And so we've modified, over the last 8 months or so of working with eWeb, we've modified our app to be more third-party friendly and support that. We're also using it out in the Snake on a sediment reduction program, and so we're trying to modify it there to work with a third party as well. So difficult, I mean, we've hired some folks with some expertise in this, and then also working with some great developers, and we are looking to make this available for others to download where there's interest. So please give us a call or an email if you do have that interest. A couple others for riparian restoration and water quality trading. How long are the agreements with landowners, and how do we ensure long-term protection? The stakeholders coming together on quality standards for riparian revegetation in Oregon all decided that 20 years was the minimum project life to ensure that the outcome was a healthy riparian ecosystem. So since a 20-year lease is easier generally to contract for than an easement in perpetuity, we start with a 20-year lease, and most of our landowners, we now have a contract for 20 years. Because there are good riparian setback regulations in Oregon, we consider this to be a pretty good indicator that these riparian zones are going to be healthy from here on out, especially because we're not generating kind of merchant saleable timber, but rather a very diverse riparian ecosystem. But if City of Medford, for example, or a temperature credit holder wants to continue those temperature credits, they or we could go back to those landowners and recontract at the end of 20 years and continue the maintenance and monitoring to those quality standards. A general question on suggestions to help a region move forward on developing a water quality trading program. I think the biggest thing is regulatory clarity. I work personally a lot with the utilities that are looking to water quality trading as a potential compliance option, and the hardest part for them is decision making with lack of clarity. And so we are fortunate enough to have some good leadership here in Oregon, from Oregon Department of Environmental Quality, on setting some very basic guidance on water quality trading for their permit writers, and then some third parties, the Willamette Partnership and others, that have built out a lot of the quality standards, and Oregon DEQ has accepted those, which has really provided that clarity not only for the utilities that this is supported by their regulators, but for us as an implementer that we know exactly how much is enough in terms of the quality standards and how and where to implement these projects. So that's the big one, I think, is really figuring out the mix of clarity that you can demonstrate, and then certainly looking for leadership from utilities on looking into these things. And it helps if there's conservation actors like the Freshwater Trust or some of your local groups. Nature Conservancy, I think, understands this very well. There's other regional groups, I think, that understand this very well that you can speak to, and that some of those groups may be willing to take on some obligations to perform watershed implementation of these programs, and that can be really key for utilities so that they don't have to do the landowner recruitment and implementation themselves. It's trying to find who's going to implement. So we're happy to speak more on that and have found ourselves as the implementer in quite a few areas regionally and looking where that may be necessary well outside of the Pacific Northwest. So I'm going to kick it over to Julia and kind of continue on some Q&A.
So one of the other questions that we have here is how was the mean phosphorus values calculated for the lower Boise? And that's a great question, and I think the second question that goes on from that was whether or not that is the load that is entering the water body, or if it's just the value that's leaving the field and how much phosphorus is actually entering the river. So the first one, the mean phosphorus value, comes from information from the lower Boise River watershed that is the phosphorus that's associated with sediment loss from agricultural fields. So that's a value that's been measured within the basin, and it's an assumed relationship between the sediment and the phosphorus. But to support that question, and to support the question of how much of that is leaving the field and how much of that is entering the water, we went through and did a case study where we took one of the smaller tributaries that's almost entirely dominated by agricultural runoff, and we looked at the water quality within the tributary itself, so right at the mouth of that sub-watershed. We have phosphorus information, sediment flow, discharge, a whole host of water quality data associated with that tributary, and we compared the measured and the modeled in that particular case. So we looked at all of the fields within that sub-watershed that were contributing potentially to water quality impairments within that tributary, and compared the measured and the model for the year's worth the year's worth of information that we had. And we actually had a very, very close relationship between that. I believe our measured and our modeled were off by approximately 10%. So really what we found was that almost everything that was leaving the field, or at least estimated to be leaving the field, was found to be entering the water body itself. So we had a really close relationship between the total phosphorus that was modeled from leaving the field to that actually entered and ended up in the creek itself. And so we had some really good information there that gave us that level of confidence that the modeled information that we had was actually pretty consistent with the measured information. And so with that, I think we only have a small amount of time left, so I think we're gonna be ready.
All right, so yeah, in the interest of time, we don't want to go over, but there's a couple more questions, and certainly shoot us an email if you'd like to get to those, and we'll reach out to you as well. We've really enjoyed sharing some of the work we've done with all of you. We hope that it can be helpful in looking at some of the issues and opportunities that are out there in the watersheds in the U.S. I think from our perspective as tool developers and tool users, we think that random acts of conservation has to end. Just in the last 5 years, our capacity as a sector, as an environmental sector, has grown immense. The models out there, our ability to store and manage data and really tease out meaning from data has really come very, very far, and we think that everyone that is out there really needs to be thinking about how to bring the way that we look at watersheds, assess, prioritize conservation actions, and reach goals. It just needs to radically improve, and I think we hope to be on the vanguard of that. We hope to help others that are looking to solve some of those same problems, because we really think that the efficient use of tools like these can really lead to achieving our environmental goals. And if we don't really grab onto some of this tech, and use it well, then we're never going to get there. So we appreciate your interest, and we hope that this was a valuable session. Thank you very much, Julia and Danielle, for your help as well, and we hope to talk with many of you soon. Thanks.
Great, thank you, Alex. And thanks to everyone for joining us today. We appreciate your participation. So this concludes today's webinar. Certainly, if you have any follow-up questions, feel free to contact us and start some one-on-one conversations. Thanks.